Hello, and welcome to part 1 of 2 on landslides and hill slopes. So in this two-part lecture, we're going to be focusing on the hazards and the risk presented by different types of landslides. And in particular, we're going to try and relate this back to places that are familiar to yourself. So throughout this lecture, we're going to be talking about the fact that risk is not necessarily the same thing as hazard. Instead, it's thinking about the hazard, the potential harm to yourself, to your community, times the occurrence, so the actual likelihood of that harm occurring. Before we really get into that and into landslides, we need to cover a few things first. So to understand the risk of landslides, we really need to understand how the material for landslides forms. So this is going to bring us to rock weathering. We need to think about how that material might move in ways that aren't hazardous landslides. So we'll talk about some diffusive hill slope processes. And then finally, the second half, so part 2 of this series, is going to talk about the different types of landslides, the different hazards that they pose, and then what controls landslide occurrence to finally get at, by the end, the idea of landslide risk. So we talk about landslides today, and we'll talk about rivers and flooding tomorrow. We're really delving into the branch of geology that is called geomorphology. And this is the study of Earth's surface. So if you break down the terms within geomorphology, see that it's the Earth's shape, the study of the Earth's shape. And this is the branch of geology that really deals with young time. So we tend to think of things that have been occurring in the last hundreds, thousands to perhaps 1 million years, rather than thinking of the full billion years of geologic time. And essentially, this is the branch of geology that thinks about erosion and deposition and really ties closely to natural hazards. We could boil down a lot of geomorphology to just asking the question, how does mass move around? And in particular, when we're thinking about landslides, we're thinking about how does soil, how does debris move around? Just to give you some examples of things that are encompassed by geomorphology, we think about glaciers. So glacial erosion is glacial geomorphology. We talk about landslides, which we'll go over today. Rivers and flooding, which we'll talk about tomorrow. But geomorphology also includes longer time scale things like mountain building, or when we go down to the ocean, we think about bluff erosion, kind of coastal geomorphology that deals more with beaches and deltas. But like I mentioned, we're really going to be focused on landslides today. And we can ask ourselves this question of how is mass moving around in the context of a hill slope? So take a second and try and identify some different ways that you think rock might be moving around in this landscape. So I identified a few ways, and I have a little bit of a heads up on y'all because I took this picture and I've been to this location. But we basically, at the top of this hill slope up here, we see that we have mechanical weathering, which is what we'll talk about first today. This is the process by which the rock, which is kind of hard rock, it's not transportable, is broken down into smaller bits of rock that can be transported. It's then transported in these steep little valleys here through a process of debris flows, which is the type of landslide that we'll talk about in the second half of today. We can also see some bare steep areas here where the rock is actually falling just under free fall and gravity. And that's another type of landslide that we'll talk about called rockfall. We've got a trail coming through here, so there is some movement by humans, and that's going to be part of this diffuse movement that we talk about in this half of the lecture. And then in the forefront here, this smooth surface, this is not actually another hill slope. This is the bottom of a large landslide that blocks the valley. So this is a type of landslide called a rotational slide or a slump, and is another one of those slides that we'll talk about in the second half. All right, so now that we've kind of primed that, I just want to let you know what's going to be due at the end of this so you can have that in mind. What I'm going to have you do is to choose a location. It can be where you're from, it can be someplace you're familiar with, or someplace you really want to go in the future. And for that chosen location, we're going to try and diagram out what the hazards are related to hill slopes and landslides, and then what the occurrence of that hazard is, so that the intersection of those two would be the definition of risk. I'll have you do a conceptual diagram of slide types. We're going to go over earth flows, debris flows, rockfall, and rotational slides. So those are slides I'll expect you to talk about. And then you'll have a 2 to 3 sentence justification. So just keep this in mind as you're listening along, that we really want to try and pinpoint the hazard and occurrence of different slide types and be able to apply that to different locations around the world. Okay, so before we really dive into that, we need to understand, how do we get the material that makes up landslides? And so for that, we need to think about this bedrock to soil transition, where the bedrock is this hard, indurated mass of rock that cannot be transported. It just makes up the earth and the hill slopes. So through a process called weathering, we're going to see this bedrock be broken up into smaller bits, and these bits may become separated and therefore transportable. As they do so, they transition to what's called regolith. So the regolith is kind of this section of the diagram where we have bits of bedrock that have been broken apart from the main mass of bedrock and now can be transported by hill slope processes. As those regolith bits break up even more through more and more processes of weathering, they eventually get small enough and have enough nutrients within them that they can support life. And that is going to be soil. So the difference between soil and dirt is that soil can support life. And we're going to find it kind of at the top of this diagram where we see roots, plants, etc. Okay, so for the next few slides, I'd like to talk about weathering, which is that process of breaking rock down into smaller pieces. It's through this process that we're going to form the material that can be moved in landslides. So understanding where weathering is going on, whether it's rapid or slow, is going to help us understand whether or not there's a potential for a landslide hazard. There are two main forms of weathering that we'll talk about. The first is physical or mechanical weathering. This is, to me, the kind of simplest one. Basically, there's no change in the rock composition. The rock is just physically breaking down. So in this diagram right below, you can see this first gray rock breaks down into smaller pieces. Through further mechanical weathering, those pieces break down into even smaller pieces, and so on and so on. On the other hand, we can also have chemical weathering, which is going to be the breakdown of chemical bonds that are holding the rock together. So if we start from that same gray rock, rather than breaking down into 3 smaller pieces that are made of the exact same rock and mineral types, we see that rock forming constituents that are all different types of minerals, as you can see by the different colors here. And so chemical weathering is really going to be dictated by chemical reactions. For example, what's shown here is the breakdown of calcium carbonate into calcium ions and acids. So we'll go through a few processes of mechanical weathering first. As I mentioned before, mechanical weathering is this physical breakup of rocks, and it occurs through processes that basically expand and contract little fractures in the rock until the fractures break. So we'll go over the process of pressure release, which is also called exfoliation. We'll talk a little bit about thaw cycles. We won't really talk about thermal expansion, but that's going to work very similarly to thaw cycles, where you basically got expansion and contraction of the rock that breaks it apart. And we won't talk about salt crystallization either, but that's another process to be aware of. As salts accumulate in water or kind of crystallize from water in the cracks of rocks, that's changing the size in the fractures between the rock, and that kind of expands and puts pressure on those cracks. A really nice diagram to explain how these 4 processes work is shown on the right. So you may start out with a solid rock here, And it's going to have some small fractures or cracks in it that are called joints. These joints allow water in as well as other liquids. And that water, through the process of maybe freezing and thawing, through maybe the process of salt crystallization, that water is going to expand and contract, which puts pressure on those joints and causes them to grow and eventually causes them to break up the rock. The rock itself can expand and contract through heating and cooling, so that's thermal expansion and contraction, and that again is going to cause those joints and those fractures to break up even more. And so through that process of breaking up, we get into kind of phase 2, where you can see those joints have really grown, and we now have really small rock particles along those former joint lines. And if we go even forward in time, you can really see how the rock is breaking down into much, much smaller pieces. Occasionally, we get some intact rock left behind. These are called core stones. One of the key tenets of mechanical weathering is that we're increasing the surface area. So as you break up a rock even more, you're forming more and more surfaces of that rock. And those are going to cause or result in more and more areas where mechanical weathering can occur. So this is a positive feedback cycle. As mechanical weathering occurs, it opens up more locations for more mechanical weathering to occur. So I wanted to go over a couple different types of mechanical weathering, partially because I think these are just really interesting weathering phenomenon. So the first one here is exfoliation weathering. This is often called onion skin weathering because it looks like an onion. And this occurs mostly in granitic rocks. And so we'll go over next week what exactly a granite is, but you can think of these as the rocks that form Pikes Peak near us, or that form the Sierra Nevadas, and that might eventually become your countertops. This exfoliation weathering results in what are called sheets of rock that are breaking apart in curved surfaces, often surrounding a larger, more intact mass of rock. So you can see those surfaces on Half Dome. We can also see them somewhat here in this picture of 11 Mile Canyon, just a couple hours west of us in Colorado Springs. And in this picture, you can see it really well. There's a person for scale, and you can see what looks like layering in this rock. And it's not actually layering. These are the exfoliation joints. So we call these exfoliation joints. You'll also see this referred to as sheeted joints. And there are a series of fractures in the rock that are forming parallel to the free air surface. And this might make more sense when we think about the process that causes exfoliation weathering. So exfoliation weathering is really going to be confined to rocks that form deep under the earth at about 10 kilometers or greater depth. So in this image that I'm annotating here on the upper right, we have at depth this large body that used to be magma and has cooled at depth to form a granite. This granite cools at greater than 10-kilometer depth. And so as this rock is formed, it is formed under high pressures where there is at least 10 kilometers of rock sitting on top of it. So that's going to be really important. That's encoded into the rock structure. However, as surface erosion occurs, so this lake, maybe a river starts to run through here and it erodes away the material on the top, that starts to decrease the pressure on top of this granite, and that causes some expansion and tension within the granitic body. And so as that body experiences the drop in overburden pressure, it starts to expand outward, as you can see by the red arrows that are already existing, as well as the red arrows I just added. And in doing so, that expansion causes cracks that occur perpendicular to the direction of expansion. And that's also going to be perpendicular to, or somewhat parallel to the free air surface. So we get a series of cracks then that form parallel to the free air surface, and these are layered and result in this onion skin like peeling or exfoliation of the granitic body or the granitic rock. So the kind of the mechanism behind exfoliation weathering is this change in pressure, where we go from high to low pressures, and that causes rock to expand. And since rock is hard and brittle, it expands through fracturing. That fracturing breaks up the rock into regolith that could then be transported. So kind of the other main processes of mechanical weathering are going to rely not necessarily on the rock changing pressure, but on pressure changes within fractures of the rock. So a common example of this is freeze-thaw weathering. So in this case, we have a rock that's near the surface. It has a series of fractures or joints in it, and those joints are large enough to let in some water. As the water enters those joints, it may freeze due to just sub-zero temperatures, and as it freezes, it expands. That expansion puts pressure on the rock and on the joints, and it can cause those joints to grow further and further break up the rock into smaller and smaller pieces and more mobile pieces that form the regolith and then the soil. The cracking of these rocks can look fairly powerful. So in this boulder here, you can see these chunks of the rock that have fallen off through freeze-thaw weathering. So this, even though the fractures themselves may be fairly small, just this kind of constant freezing and thawing within those fractures causes a lot of breakage of this rock. And if this continues for a long period of time, we may get things that look like the right picture, which is called Felsenmeer, or a sea of rock. And this is just a whole hill slope of rock that has been broken up by freeze-thaw processes and is now just kind of sitting there waiting to be moved. All right, so that was an example of two main mechanical weathering processes by pressure changes of the rock, as well as expansion and contraction of material in the fractures of the rock. The other type of weathering is called chemical weathering. And here, rather than the rock breaking down into just smaller bits of the same rock, we're going to have transformation or decomposition of minerals into another type of mineral. So rocks are made up of minerals, and if these minerals change, then the rock composition changes. There's two main subtypes to chemical weathering. We can have the type where the minerals just dissolve, for example, in carbonates or limestones. Oops. In limestones, the carbonate mineral that makes up the limestone rock, when it reacts with a slight acid, is going to dissolve. And that's just going to dissolve away into ionic constituents. So we're not going to leave behind a different type of rock. We're just going to leave behind a hole. And you can see that in these limestone bricks here, where there's been some of this carbonate dissolution weathering, and there are these large holes as that carbonate has dissolved away into ionic constituents, which then run off into the groundwater or the surface water. The other type of chemical weathering is going to take a primary mineral and turn it into a secondary mineral. And so there's still going to be material there. So unlike the example of the limestone dissolution, there's not a hole left behind, but we're leaving behind a different type of rock. In most cases, these primary minerals are going to weather away into clays. So just as we may colloquially think of clays as a kind of a sticky substance that maybe you can mix into pottery, clays are a type of mineral that are exactly what you use in pottery. So this is a nice example where the way we think of clay colloquially as non-scientists is kind of the same way we're going to think of clays as a scientist. So this is important to remember that through chemical weathering, we can get ionic. We may lead to ionic constituents in water, or we may lead to clays. So in week 2, when we talk about sedimentary rocks, this is going to be important to remember, to recognize that a lot of what's going on the surface of the earth is making clays. And those clays may make more rocks. But beyond that, let's summarize what we know about weathering. So there's going to be 3 main controls on whether or not weathering can occur. And this is important to keep in mind, as we've mentioned before, because weathering is going to lead to the loose material that could form the potential for hill slope failures and hazards. So the first of these controls is surface area. As more and more of a rock is exposed, there's more and more surface of that rock that's exposed to weathering processes, whether it's chemical or mechanical. So really nice mathematical example of this. If we start out with a 1 by 1 by 1 meter cube, the surface area here is 6 square meters. However, if we were just to form 2 fracture planes that cut it in half, I guess we need 3 fracture planes that cut it in half, we'd end up with a surface area of 12 square meters. If we had divided it up into 3s on each plane, that would end up with 18 square meters. And then finally, if instead of breaking it up evenly, we had just taken material off of the corners, and each of the material that's taken off of that corner has its own surface area. This results in scenario 4, where starting from 6 square meters of surface area, we now end up with 2.5 acres of surface area, or 10 to the 4th square meters. So as we get more and more surface area, we have more and more weathering. The other main control on weathering is going to be the climate. And so we can think of that as the temperature and precipitation or moisture characteristics. When it comes to chemical weathering, this is going to be important in terms of dictating the speed of chemical reactions. So these chemical reactions are probably going to be faster when we have warm climates, and also when these climates can be slightly acidic. That's going to help break down our carbonate rocks. So we can find this in areas that are warm and moist. Places that have a lot of vegetation that decaying is also going to help speed the rate of chemical weathering. And we tend to see, the opposite of this, areas with not a lot of vegetation, areas that are cold. So polar regions tend to have very slow or no rates of chemical weathering. Temperature and moisture are going to affect mechanical weathering. As we talked about earlier, freeze-thaw cycles are really important in mechanical weathering. And so areas where you have some moisture to get into the fractures within rocks, and then areas where you have temperature swings large enough to get freeze-thaw cycles are going to be really conducive to mechanical weathering. All right, and finally, time is another large control on weathering. The longer rocks sit around, the more time that they've been exposed to weathering, and therefore the more weathering will have occurred and more soil and regolith will have been produced. So this means that landscapes that have been recently formed will have had less time for weathering and may have less soil for erosion by landslides or by other processes. So this could include areas that have recently had a glacier. So glaciers are going to scrape off all of the loose soil and regolith and leave behind that bedrock that needs to then restart the weathering cycle. It could include places that have been very recently formed, like young mountain ranges or young mountain ranges compared to older mountain ranges. However, I'd like to note this first example here, we're thinking on the scale of millions of years in terms of age. So this would be, saying that a young landscape, so a young mountain range, will maybe have only had 5 million years to weather versus an older mountain range, which would have had 50 million years to weather. So in either case, we're still thinking there's still a lot of time there, compared to being scraped raw by glaciers could occur in the last 15,000 years. Okay, so to kind of bring this back together to hill slopes and also into kind of agricultural usage, thinking about where the soil is. So areas where we're going to have more weathering are going to produce more soil products. And so think about, across the globe, where are the conditions that would lead to greater weathering rates? So try and identify one location that you think would have a lot of soil and one location where you would expect to see thin soils. All right, so one location that's going to have thick soils would be the Amazon basin. So this is an area that's going to receive a lot of water and has a lot of precipitation, and it's fairly warm. So there are rapid chemical weathering rates that have created really thick soils and soils that contain a lot of ions and a lot of nutrients. In contrast to this, if we go up closer to the polar regions, we may see a lot of mechanical weathering. So we could see some felsenmear and seas of rocks, but in those cases, we may not see the breakdown to soils. We may not be getting that chemical weathering that's going to spread nutrients and ions throughout the soil. Okay, so this moves into thinking about, now that we've created the material that could potentially move in a landslide, how does it actually move and when is it hazardous? So we're going to talk about two different ways that material can move. The first is going to be diffusion, and then in the second half of this lecture, we're going to focus on advection, which is the landsliding. And just to show you what I mean by these two terms, we're going to watch part of a small video on this sinkhole dye tracing experiment. All right, so this is a river that has a lot of sinkholes in it, and in order to figure out where the water goes from the sinkholes, the scientists are releasing a bunch of dye into the water and tracing where the dye goes. So they're releasing the dye kind of in this upper section. We'll see it more clearly once it starts to move. There we go. So they're releasing it. It's going down this sinkhole and flowing downstream. All right. So as it flowed downstream, this dye was subject to advection and to diffusion in the same way that the mass on our hill slopes is going to be subject to advection and diffusion. So advection is a velocity-driven process. So that is where the river water is moving downstream and it is carrying the dye with it. And you can see that in all of the movement of the dye away from its main source and kind of this linear line of dye that is moved downstream. Diffusion is going to try and spread out the concentration of dye with areas that don't have any dye, and it's a much slower process. And we can see this occurring mainly at the edges of the green plume, where rather than being solid green, we see some places where it's kind of transitioning from a solid green to a mixed green, gray, brown, and then eventually to the brown, gray water. And so that's going to be kind of more of a slow process that's driven by gradients. So in this case, it's a gradient in concentration. When we think about hill slopes, it's going to be driven by the actual gradient of the hill slope and trying to even out the gradient until you have a uniform hill slope. Versus advection, which is really driven by velocity processes. So when we think about hill slopes, this is going to be our landslides that are occurring very rapidly. They're occurring under conditions of a sort of gravitational failure rather than trying to balance out what the slope is. Okay, this might make more sense as we start to look at these processes in detail. And so before we do this, though, I wanted to back up a second and talk about the overall theme of today, which is landslide risk. So now that we're getting into different types of hill slope movement, this is a good time to assess what hazards are versus occurrence versus risk. So the hazard is going to be the potential source of harm, and the hazard may have a different frequency depending where you are. And so that frequency dictates the occurrence, and those taken together inform the risk, which is that chance of the event harming you. All right, so an example of this would be crossing the street. We know that every time you cross a street, cars are a hazard. They can hit you and cause loss of life or other bodily injury. But we kind of internalize that occurrence to inform our risk. So if we're crossing a really busy highway, we know that we definitely want to look both ways. We're very cautious because we know that there are a lot more cars, so the occurrence of that hazard is a lot higher. Versus if we cross a country road, we know that that risk is fairly low, so we may look both ways, but we're going to do it much more quickly. We may not do a double or triple check because there's kind of a low occurrence of that hazard happening, resulting in a low internalized risk. So we'll try and think about these concepts in relation to hill slopes over the rest of this lecture. And the first hill slope process that we'll talk about is diffusion. So as I mentioned, this is sort of the slower process by which the movement of soil and of rock is trying to even out the hill slope. Right, and what I mean by this is, I'll try and draw it in this corner. If we have a hill slope that is fairly steep and it has two kind of a top edge and a bottom edge, the process of diffusion wants to just create a nice linear slope there. So the slope across the whole place will be equal by the time diffusion is done. What this means is we're going to tend to have material from this top part being transported down to this bottom area in order to even out the slope. A really common way we can see hill slope diffusion in action is just walking around neighborhoods and looking at retaining walls. So these are these concrete or rock walls that are holding back an elevated lawn. There's a large slope break there, right? You go from one slope suddenly to 90 degrees to a fairly horizontal slope. And so by the process of diffusion, the soil is trying to even this out. And if these retaining walls aren't built correctly, they will start to tilt as a result of that hill slope diffusion, right? So it's one way we can see this in action. But we can also look at the different sub-processes that are occurring. And so we're probably seeing in those last few slides was a process of diffusion called soil creep. This is kind of what it sounds like. The soil is just slowly creeping along in a downslope direction. It tends to occur on slopes that are greater than 5 degrees and is really just gravity pulling the soil materials downslope. It's going to occur more rapidly towards the top of the soil and then much more slowly as we get down into the regolith and towards bedrock. And it causes some bending or distortion of the features on the surface. So one way to look for this would be, we just talked about these broken retaining walls, but another way would be to look at the trees that are on this hill slope. So the trees want to grow with their trunks upright. However, if their base is continually moving with this creep process, we're going to see a distortion of the tree trunks that forms this curved pattern. And this is really indicative that there's some soil creep going on in the subsurface. Related to soil creep, and maybe not something we'll see here, but if you're in more polar regions, you would see more often, is a process called solifluction. So this is somewhat similar in that we have movement of the soil downslope by gravity. However, here we tend to see this in permafrost landscapes, and so there's seasonal melting of some of that ice, and that seasonal melting can cause much more rapid movement. And so we get this solifluction, which looks a lot like the landscape just dripping on itself, which is a result of a gravity-driven movement of soil downslope that's aided by that frozen ground freezing and thawing throughout the year, which kind of makes it, kind of lubricates the subsurface so the soil can move a little bit more quickly. Moving back to a diffusion process that we probably see more commonly here and more commonly anywhere where there's rain is going to be the force of rain splash. So as rain particles fall on the ground and an individual raindrop, it's going to dislodge some material as it impacts with the ground. And that material is going to be projected into the air. And then as it falls down, it's going to fall down under the force of gravity. And so if this raindrop dislodges material on a hill slope, that means that everything that's dislodged is going to preferentially fall downslope. And so slowly but surely, through the force of a single raindrop multiplied by millions, you get this constant motion of small soil particles moving downslope. This is, because rain particles are limited in size, we really see this acting on things like silts and clays. So really, really small particles. But a really nice example of this, if you go out after a rainstorm, particularly in Colorado Springs, when we get our summer thunderstorms, go out to a place like maybe Sonderman Park or go out along the river trail, and you'll see these little pedestals forming where you have, a kind of maybe sand or pebble, and it's sitting on top of clays and silts. And this is a really nice sign of rain splash, because what happened was originally the clays and silts were at the same level as that pebble. And during that rain event, they were eroded away by rain splash down to their current level. However, all of the clays and silts that are under these pebbles were protected, kind of like those pebbles or those sands were acting like umbrellas. And so they don't move, and you get these pedestals forming. Right. Also related to rain, another type of diffusion process is overland flow. And we'll talk a little bit about this tomorrow when we think about hill slopes or think about rivers, because this is kind of the first process before we actually get a river. In overland flow, after a rain event or snow melt, we may have water moving over the surface of the landscape, and it's not channelized. So this is different than a stream or a river moving over the surface of the landscape. But this overland flow, it does have some motion to it, and it can pick up some particles. And so we do get a bit of surface erosion occurring after this. You can see this in this picture on the lower left here, where the light tan areas are areas where overland flow has picked up some ground particles. And in between those locations, kind of the deeper brown, you can see the islands that were left behind. We see this overland flow diffusion particularly strongly after wildfires. This picture on the lower left, again, is an image after wildfire. And this is because overland flow tends to occur after wildfires, as the burn area tends to be hydrophobic. Which means that it repels the water. And in doing so, it causes the water to run off along the surface instead of seeping in to the ground. All right, the last diffusion process that we want to mention, because it's going to be fairly important as we think about hazards and risk in areas that we live, are humans. So through human processes, whether it's walking on a trail and dislodging some particles in that way, or walking between switchbacks on a trail and dislodging particles, or if it's plowing, terracing, and larger scale construction, these are all moving soil mass and moving particles of the hill slope. We may be directly moving the soil and rock downslope, or we may indirectly be doing it and sort of priming it for another diffusion process. For example, in this lower left picture of plowing, this loosens the soil particles and it makes it easier for other processes like overland flow or maybe some wind to carry that soil and move it downslope. All right, so that's the end of part 1. We've talked about diffusive hillslope processes, and we've talked about different ways in which material on hillslopes is formed through weathering. So as we end, I'd like you to consider, before you transition to part 2, diffusive hillslope processes tend to be less hazardous because they tend to be slow moving. So based on the hillslope processes that we just covered and that we just talked about, where in the world would you expect to find these slower movements? We're going to contrast this in the second part by thinking about where would we expect to find fast hillslope movements.